Welcome to part 2 of the worksheet video on reduction. We will continue from where we left off in the first part of the video. Let's see how to find the shortest path in our graphs. By definition of diameter, we know that we are looking for the maximum of the shortest distance between any two vertices. So let's look at the shortest distance first. To find the shortest path from a starting point to an endpoint, we need to keep track of all the vertices in between. When traversing the vertices in the graph, how do we know which vertex should be part of the path? More specifically, given all the vertices we have visited so far, which vertex should we choose to check and update the distance from the starting point to its neighbors? Let's look at this. While x and y can be a part of the shortest path from S to T, which path has the most potential? Obviously, S, A, X, because two edges are less than three edges. In this question, all weights of edges are equal to 1, which means the number of edges between any two vertices is exactly the distance. Therefore, we only need to count the edges between them. So any vertex which is adjacent to the starting point, we know the distance is 1. Any vertex which is adjacent to the vertices we just talked about, we know the distance is 2. And we do the same for the neighbors of these points, they'll be 3. It looks like we are incrementing the distance every time we meet a new generation of vertices, or new layers. Do we have such an algorithm that traverses the graph by its layers? BFS. We can use BFS to find the shortest distance. The original BFS does not return anything related to distance, so we need to make some modifications. Since we are looking at the simpler question where we only need to find the distance between two vertices, the modification is relatively simple. In the code where arrow points to, when we traverse the neighbors of the vertex that we pop from the cube, we know that these neighbors should be one level lower than our current vertex because they are adjacent to our current vertex. So other than marking them as visited, we also want to update the neighbor's distance based on the distance of our current vertex. And don't forget, after the queue is empty, we need to return a set of distance because that's what we need to find. This set should contain the shortest distance from start vertex to all vertices. Now we have a function findThis, which find and return the set this, store the shortest distance to each vertex. The findThis function here must take big O of v plus e times to satisfy the question requirement. Due to the time constraint of this video, I won't provide the details of this modified function. To get a Series 31 one-up, please try to figure out pseudocode as take-home exercise. We will provide the correctness of this conclusion later on in the lecture. For those of you who want to stay ahead, check out textbook section 3.2 for details. Is this the reduction we need in this question? Is this map this the question asks for? Now, when I ask that, you should know we are not done. Let's go back to the definition of diameter. We know that we are finding the maximum of the distance between u and v, and each of them can be any vertex in the set V. And what does our findThis do? We compute and find the shortest distance from the starting point to all the vertices. Does anyone see what the problem is? And how do we fix it? I'm going to mute myself for 5 seconds for any of you who would love to think. While diameter looks at the distance between any 2 points, our findThis only focus on one starting point. Does it mean everything we have done before is meaningless? No, it's not. When we want to find the diameter, we are finding the distance between any two separate vertices. Now I'm going to separate the formula of diameter to make it easier to see what we need to do to reduce the diameter to distance BFS compute. Now here we can see we pick vertex u in our outer max, and in inner max we want to find the maximum of all the distance from u to any vertex v different from u. And I'll find this literally compute the distance from the given vertex u to all the vertices. In our find this, we return a map which stores all the vertices that are different from our starting vertex. So for the inner max, we just do a linear scan to find the maximum of the set disk. And to do the outer max and get the overall diameter, we just apply our inner algorithm to all the vertices u in the set V. These two reductions lead us to the following algorithm. If BFS only find the distance from one starting point, what if we run BFS on all the vertices, and then we pick the largest return values of all the map of distance? We declare a variable to hold the diameter and initialize the 0 at the beginning. For each vertex v in the graph, we run our findThis function starting at v. It should return a map. We then use the function max to linearly search for the maximum of this map and return it in the variable temp. We replace current diameter with temp if the new maximum is greater than the current maximum we hold. This makes sense. We guarantee that here we are measuring the distance between any two vertices because at each starting point, we run BFS to traverse all the vertices. Here we can see the power of reduction because the idea of reduction we are making is general and straightforward. If the condition of question in part B is changed, we can keep the peripheral code and only replace the findThis function with our new algorithm. More generally, we can use any algorithm other than BFS inside our function call if it can compute the distance. So far, we have gone through a lot of steps to solve a problem similar to what we'll see in CSC 331. And now it's time to put it all together and build the things we need as a solution. I think most people are confused about the difference between algorithm idea and algorithm detail. Algorithm idea is the idea of how to come up with this algorithm correctly and how this algorithm works to come up with the return value. Algorithm detail should include all the details of how your algorithm runs. It should include how you transform the input and output, if applicable, variable initializations, all the steps. Pseudocode is always the best choice and won't be wrong. In this question, the algorithm idea is what we just talked about and more like a natural way. The idea of shortest path. Why BFS works here. We learned this from textbook sections 3.2 and our modification. How to reduce one maximum to our BFS stuff. And how to use it to find the diameter. You don't have to make sure that a random person on the street can guess what you're doing, but you should at least make sure that any CS student who is taking 250 data structures or 191 discrete maths can understand it. Here's an example algorithm idea and algorithm details. Feel free to pause it if you want to take it as reference for your future homeworks. The algorithm detail should contain all the details of how your algorithm reads the input, computes, and returns the output. It's better to use pseudocode in this part. Here, I'm just collecting all the pseudocode I have shown before and put it in all together in one place. And the pseudocode for findThis is the take-home exercise I leave you all with. We build an algorithm and let's see what the output looks like. At first, we need to use an array or map this to save the result. In this example run, we set our start vertex as the red vertex Maryland. Using findThis, we compute and store the shortest distance from Maryland to all the vertices in the map disk. Maryland to itself is just 0. Pennsylvania is the only neighbor of Maryland, so the distance from Maryland to Pennsylvania is 1. New Jersey, Delaware is 2. New York is 3, Vermont, Connecticut, Massachusetts is 4, Rhode Island, New Hampshire is 5, and Maine is 6. We notice that the maximum value of the distance is 6. Based on this map, we now know that the maximum distance from Maryland is 6, which is Maryland to Maine. Now we choose another star vertex, for example, Rhode Island. I'll skip the details and tell you that the maximum distance from Rhode Island will be less than 6. And you can try using any star vertex, and you will see that 6 is the maximum we can get. So the diameter of this graph is 6. We prove that our algorithm is correct. Really? If I give you a different graph, how do you know this algorithm can compute the correct result? Another demo to show me how this works again? What if I give you another, and another? Showing an example run is absolutely the wrong way to prove that your algorithm is correct. It's fine to use a counterexample to prove something is wrong. Please check out Mary's video about proof by contradiction and counterexample for this. Never ever use any specific example to prove the correctness of your algorithm, because you show this work only for finite state. I promise you will get 0 if you do that, so don't do this. When we say we want to prove an algorithm is correct, what we mean is that it should work correctly for arbitrary input. But it is impossible to run our algorithm for infinite kinds of graphs. So we should use math and logic to convert it into a general pattern. The general proof techniques like induction, contradiction, etc., of course, we like to use them. But if we have the will, why don't we just use it? The QR code is the web page about reduction as 331 support pages background material. And we'll use the example in here. Suppose there's a single cell that divides into 2 identical cells in 1 second. After s seconds, we know that we will have 2 to the s amount of cells. In the web page, we prove that this is correct by connecting the pattern of reproduction to the leaves in the binary tree. Each time the cells divides into 2 children, it is the same as adding 2 leaves onto the parent. Notice here the example using Ts for any s greater or equal 0. We need to generalize our logic when proving something. Again, don't use specific values. After connecting it to the binary tree, we apply the knowledge we know by saying, in 250 data structures or 191 discrete mathematics, we know that a complete binary tree with high s will have 2 to the s leaves. So our claim 2 to the n cells is correct. In homework and exams, when you want to cite something to support your argument, you need to cite it exactly. If it is a lecture slide or a lecture note, you need to specify the date or a lecture number. If it is from a textbook, then add page number or a section number. Add post number if it is a Piazza post. You cannot just tell people, hey, go find it in the textbook. Remember, mention the name of your collaborators or use noun if you finish the homework by yourself. Also, I strongly encourage you to use the Provide LaTeX and Microsoft Word template. Choose the one you feel comfortable with so you don't have to worry about losing points because you forgot to cite your source or mention your collaborators or didn't separate your algorithm idea from the detail. We know that diameter is just the maximum of shortest distance. And shortest distance we know we modify BFS to compute it. And this is correct because we learned it in the lecture number. If you are watching this video, maybe you haven't started the lecture yet. But let's say we're going to talk about this in a lecture later. And you can also find it in the textbook chapter 3.2, Graph Connectivity and Graph Traversal. It's another story to tell how to come up with the proof idea without a specific question. But in reduction, since we have something correct, we can either start with our correct black box algorithm and then use induction or direct proof to say that our algorithm is also correct. We can also prove it by using contradiction. Assume our algorithm is incorrect. Then there exists another vertex, u prime and v prime, and the shortest distance between them is greater than the result our algorithm returns, let's say duv. If this path exists, it should be computed and returned by our find dist starting at u prime, and replace our result in function find diameter. Based on the result returned by our algorithm, this path exists but was not computed by BFS, which means that BFS could not find the shortest distance. And we know this isn't true because we learned it in the textbook chapter 3.2. The beauty of contradiction is that when we dig in the logic, at some point, we will say that our black box algorithm or any correct thing is not correct. And what I just talked about is literally the proof idea. It is in natural language, but it follows the logic. It tells the grader and everyone that which proof technique you're gonna use. Contradiction. What you're gonna assume. The result is incorrect, and there exists an optimal result. And where will contradiction happen and the reason why, and which lecture do you want to use to support your argument? Similar to algorithm detail, proof detail should be formal and logic consistent. Since we already have the proof idea, now we just need to fill it out and make it become a complete proof detail. Again, state the proof technique you would like to use at the beginning. In proof detail, we need to refer to the fact, the definition, or our assumption to go to the next step. Here, we use the definition of diameter to tell the reader that there exists another optimal result S prime if our assumption is true. You can define some notation like u prime, v prime in your solution for convenience. The S prime is not in the set returned by find dist, starting with u prime. Otherwise, the linear search in find diameter will find it and replace our result. But based on the fact in the textbook, BFS correctly computes and returns the distance S prime between u prime and v prime, which is a contradiction. The red highlighting part is crucial because we want to make sure that this algorithm only works when all the edge weights are equal to 1. You will notice that none of my proof ideas or proof details talk about the example graph or any specific graph we have, because we want to use our logic to prove that this algorithm is correct for any input. Again, don't use a specific example in your proof. It won't work. Now let's take a look at the runtime of our algorithm. We first look at find dist. Earlier, I mentioned that the function find dist can be implemented in big O of v plus e times. So the total runtime of find dist is just big O of v plus e. And in find diameter, since we run find dist on each vertex, which is n iterations, and for temp equal max find dist graph.v, find dist takes big O of v plus e times, and the max function linearly searches through the set of distance map with size of v, so the max takes big O of v. Overall, big O of v plus big O of v plus e is still big O of v plus e. So the total runtime of find diameter is big O of v times big O of v plus e, which is big O of v squared plus ve, and it's the same as the question requirement. If you have any questions about this video, feel free to come to office hour or post them on Piazza.